July 17th, 1944. Normandy, France. At 0640 hours, 5 Panzer IV tanks of the 12th SS Panzer Division crested a ridge overlooking Saint-Lô. Within minutes, they encountered 14 Sherman tanks. After action reports documented a German commander's words, "Where do they keep coming from? We destroy 10, 20 more appear. It's as if they grow from the ground itself." By day's end, 3 of the 5 Panzers were burning hulks, while the Sherman column kept advancing, fresh replacements already en route from Omaha Beach. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The weapon was America's standard medium tank, the M4 Sherman. Introduced just 3 years earlier as a symbol of industrial might and democratic resolve. Designed to overwhelm the enemy not through individual superiority, but through sheer, unstoppable numbers. Yet by 1944, this tank became something German commanders could scarcely comprehend. How did America's M4 Sherman, criticized by Allied tankers for its thin armor and modest firepower, become so numerous that it overwhelmed the technically superior German Panzers? November 15th, 1940, Detroit, Michigan. On a design bureau table at the Detroit Tank Arsenal lay blueprints labeled Medium Tank M4. The United States Army demanded a weapon to replace the outdated M3 Lee, considered inadequate after reports from the European theatre. Expectations were clear: reliability, ease of production, and the ability to be manufactured in previously unimaginable numbers. But reality already favored the Americans in ways the Germans couldn't grasp. America's crude steel output in 1940 was roughly 60 million metric tons, compared to Germany's 22 million metric tons. Industrial capacity, essential for mass production, was already shifting into high gear under the Defense Production Act. The M4's design was deliberately simplified with standardized parts, interchangeable components, and production methods borrowed directly from automotive assembly lines. Early tanks from Detroit and Lima Locomotive Works were well made with cast hulls, precision-machined transmissions, and quality control that ensured consistency. Each tank was thoroughly tested, inspected, and approved. The design was fundamentally practical. It used a medium-velocity 75mm main gun, Continental R, 975 radial aircraft engine, and an HVSS suspension system. The Sherman weighed approximately 33 tons, achieved speeds of 25-30 miles per hour on roads, and carried a crew of 5. Early models featured a distinctive sloped glacis plate, cast-rounded turret, and the easily recognizable vertical volute spring suspension. An archival fragment from the Ordnance Department Bulletin of 1941 states, the M4's production schedule must allow for 1,000 units per month by mid-1942. Any design elements that impede this goal must be simplified or eliminated. The tank's strength depended entirely on production velocity. The higher the monthly output, the more overwhelming the numerical advantage would become on the battlefield. Engineers at the Army Ordnance Department understood this completely. Production initially centered on Detroit, Lima, and later Grand Rapids, with additional factories being converted from automobile and locomotive plants. Quality control was standardized, rejection rates were minimal. The cost per tank was approximately $44,556, less than half the cost of Germany's Panther or Tiger tanks. The cause and effect relationship was already visible. Adoption of simplified design required standardized components and interchangeable parts. Any adjustment to enhance battlefield performance had to be balanced against production rate impacts, and the production rate was already accelerating beyond anything Europe had ever seen. Within 3 years, the same basic design would be manufactured across 11 separate factories, simultaneously. Detroit Arsenal, Lima Locomotive Works, Pressed Steel Car Company, American Locomotive, Baldwin Locomotive Works, Pullman Standard, Chrysler, Federal Machine and Welder, Ford Motor Company, Pacific Car and Foundry, and Montreal Locomotive Works in Canada. The tank that began as a symbol of America's industrial ambition would become a numerical sledgehammer. But in November of 1940, none of that was visible to the Germans. The blueprints were practical, the prototypes were functional. Germany believed its panzers would dominate through quality and crew training. They had no concept of what was about to hit them, or how many. March 1941, Aberdeen Proving Ground, Maryland. Range cards showed side-by-side comparisons. M4 Sherman versus M3 Lee, the tank it was replacing. Engineers recorded reliability metrics, maintenance requirements, and crew ergonomics. Results confirmed expectations. The Sherman achieved 85–90% mechanical reliability rates during extended testing. Maintenance accessibility was dramatically improved over previous designs. Components could be removed and replaced with minimal tools or specialized equipment. Drivetrain tests showed the Continental R975 radial engine provided adequate power with minimal specialized maintenance requirements. Factory journals recorded the daily output projections, 12 tanks per factory per day by 1942. That production rate was unheard of in European manufacturing. Early production was limited to validation units. Only 1,500 Shermans were built before Pearl Harbor. All were allocated to training units and the British under Lend-Lease. America's pre-war manufacturing approach mirrored automobile industry standards. Hull sections were welded by semi-skilled workers using standardized jigs. Turrets were cast in massive foundries, requiring minimal machining. Engines were adapted from existing aircraft designs, allowing aircraft engine manufacturers to transition to tank production with minimal retooling. Component interchangeability was enforced across all manufacturers. A transmission from Detroit would fit perfectly in a tank assembled in Lima. This level of standardization was unprecedented in tank warfare. German tanks required hand-fitting of components, with parts often not interchangeable, even between tanks of the same model from the same factory. The Sherman relied on America's industrial philosophy: standardize, simplify, and mass-produce. An Aberdeen testing report from this period noted M4 armor thickness adequate against standard 37mm and 50mm anti-tank rounds at expected engagement ranges. Increased thickness would reduce production rates unacceptably. This was the first documented hint of the trade-off that would define the Sherman's battlefield performance. Engineers flagged the danger of rushing too many design improvements. Any change required retooling across multiple factories. The cause and effect chain was already forming. Simplified design enabled mass production. Mass production created numerical superiority. Numerical superiority would eventually overwhelm any qualitative advantage. Even in early 1941, production engineers understood this, and tactical requirements would never override production capacity. The design was adequate. The manufacturing process was proven. The alloy pipeline was virtually unlimited. That balance between battlefield adequacy and production velocity would compound under wartime scaling. America had built an acceptable tank. Now it would build tens of thousands of them with an efficiency that would shock the world. That was something the Germans could not comprehend. December 1941, Warren, Michigan. A production schedule pinned to a factory office wall at the Detroit Tank Arsenal showed a dramatic leap from roughly 1,000 tanks produced in 1941 to 14,000, planned for 1,942. In the first months after Pearl Harbor, demand for tanks soared. The War Department planned to equip over 90 divisions, approximately 25,000 tanks by 1,944. Existing arsenals could not meet this demand alone. Factories expanded rapidly. Chrysler converted automotive assembly lines to tank production. Ford Motor Company built a massive new tank facility at Grand Rapids. Railroad manufacturers like Pullman Standard and Lima Locomotive Works shifted from railroad equipment to armor. But scaling production this fast brought predictable innovations. Workforce training accelerated as experienced automobile workers were taught tank assembly techniques. Women entered the industrial workforce in unprecedented numbers, comprising nearly 40% of the tank production labor force, by 1943. Power generation expanded to meet industrial demands. Machine tools were standardized and simplified to allow for 24-hour production. Technical markers of improvement appeared early. Internal debates focused not on whether to maintain production, but how to improve it while maintaining velocity. Welding techniques were refined to increase speed without compromising structural integrity. Cast components replaced welded assemblies, where doing so reduced assembly time. Electrical systems were standardized with color-coded wiring harnesses for rapid installation. Heat treatment cycles for armor plate were optimized for throughput rather than maximum hardness. One by one, production bottlenecks were identified and eliminated. Not all at once, not uniformly across arsenals, but the trend was clear. A Detroit Arsenal Engineers report from February 1942 noted, daily output has reached 16 units per shift. Transition to 3 shifts will yield 45 to 48 tanks per day from this facility alone. This was a production breakthrough. 48 tanks per day from a single factory meant more tanks rolling off one assembly line every week than Germany produced across its entire tank industry in a month. Proper production of a Sherman tank required 3 key stages. First, component manufacturing, including hull, turret, engine, transmission, and armament. Second, subassembly of major systems, power pack, suspension, and turret assembly. Third, final assembly where all components came together in a moving assembly line modeled directly after automobile manufacturing. Each stage was optimized for speed without sacrificing functionality. Operational testing revealed the consequences. North Africa's heat and sand exposed every design limitation but validated the production philosophy. Several captured German reports examined by Allied intelligence showed growing concern about American production capacity. One Panzer commander wrote, "We destroyed 7 Shermans yesterday. Today 12 more appeared in the same sector. Where are they finding so many tanks?" The cause and effect relationship was now visible in the field. Manufacturing velocity under wartime pressure led to consistent output and predictable quality. Those factors created battlefield persistence. Operational persistence eroded German tactical advantages, and loss of advantage meant panzer units could no longer guarantee local superiority. The first large field test in the deserts of North Africa exposed what blueprints couldn't predict and what factory inspections couldn't measure. The Sherman wasn't winning through technical superiority. It was winning through relentless, inexhaustible numbers. German tankers were about to discover that their technically superior panzers were only as effective as their production capacity allowed, and that capacity was about to be overwhelmed. America's tanks were rolling off assembly lines faster than Germany could destroy them on the battlefield. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now, back to the story. April to May 1943, Tunisia, North Africa. A British 8th Army maintenance section arranged 15 captured Panzer TOIs and IVs alongside 25 damaged but repairable Shermans. Each tank had an assessment form attached to its side: serial number, combat hours, damage assessment, and parts requirements. The expectation among Allied commanders was straightforward. The Sherman was America's standard tank. It should be quickly repaired and returned to combat. Reality validated this expectation. Of the 25 damaged Shermans, 21 were back in action within 2 weeks. Standardized parts, interchangeable components, and simplified repair procedures meant that even heavily damaged tanks could be cannibalized to repair others. The German tanks told a different story. Of the 15 captured Panzers, only 3 could be made operational using available parts. The others required components that weren't interchangeable between models or even production batches. British Technical Report number 27, dated May 1943, documented the findings. Sherman recovery and repair rates exceed 80% under field conditions. Component standardization allows single tanks to be assembled from parts harvested from multiple damaged vehicles. The comparative context made the production advantage more striking. Panzer repair depots required specialized tools and factory-trained technicians for many repairs. Shermans could be maintained by mechanics with basic automotive training using standard tools. Technical analysis revealed the core advantage. Standardized parts and systematic documentation meant any Sherman component could be replaced in the field. A damaged Sherman might be back in action within hours. A damaged Panzer often required factory-level repairs. The cause and effect chain was now documented in field conditions. Standardized manufacturing from simplified design meant parts from one Sherman worked perfectly in another. Tanks damaged beyond repair became parts donors for others. Mechanics could swap engines in 4 hours using basic equipment. Transmission replacements took 6 to 8 hours rather than the days required for Panzer repairs. Field maintenance became a force multiplier. The Germans were losing Panzers permanently from damage that Americans and British could repair in a day. American production reached 2,000 tanks per month by mid-1943. German factories struggled to produce 200 Panzers in the same period. Field maintenance parties adapted to this reality. They established forward repair depots that could replace an engine, repair track damage, or even swap out a damaged turret within hours of a tank being damaged. They used interchangeable components to keep more tanks in combat. They standardized repair procedures across all theaters to ensure consistent results. None of these advantages existed in the German tank forces. By mid-1943, entire American tank battalions could be re-equipped within days after heavy combat. German units required months to replace losses. The Sherman had established an insurmountable advantage, not through armor thickness or gun caliber, but through the unstoppable mathematics of industrial production. A tank destroyed was only truly lost if it couldn't be replaced. The American tank, the weapon meant to symbolize industrial democracy, had proven its fundamental concept. It didn't need to win tank versus tank duels. It only needed to keep coming, wave after relentless wave, until the enemy had nothing left to fight with. The jungle of steel growing from Detroit's factories had become a force that even the vaunted Panzer divisions could no longer resist. No matter how many they destroyed, more kept coming. July to August 1943, Sicily, Mediterranean Theatre. The 1st Armoured Division's Maintenance Battalion established a forward repair depot near Syracuse. Dozens of damaged Shermans arrived daily, most with track damage, some with penetrations from 88mm guns, others with engine or transmission failures. The goal was simple: repair what could be fixed quickly, cannibalize what couldn't, and keep as many tanks in combat as possible. But the plan succeeded beyond German comprehension. Records from the 1st Armoured Maintenance Battalion documented the achievement. 76 Shermans returned to combat within 72 hours of damage assessment. 14 tanks assembled from parts of 28 severely damaged units. American Army regulations established an entirely new approach to tank warfare. A Sherman was never truly lost unless its hull was completely compromised. Every other component could be swapped, replaced, or rebuilt. That assumption was based on the steady flow of replacement parts, but those parts were arriving with a regularity that German logistics officers found impossible to believe. Reality in the field was transformative. Tank crews reported that damaged Shermans were often back in action the same day if the damage was minor. German intelligence summaries from captured documents expressed growing alarm. American tank strength does not diminish proportionally to recorded kills. Units return to full strength within days of major engagements. The technical link was clear. Standardized components combined with forward maintenance depots created recovery rates approaching 70%. Tanks that would have been abandoned by German forces were back in combat before the next major engagement. The cause and effect spiral was inescapable. Simplified design led to mass production. Mass production led to component availability. Component availability led to rapid repair. Rapid repair maintained combat strength regardless of losses. Maintained strength meant constant pressure on German units that couldn't replace their losses. Unit-level innovations accelerated this advantage. Maintenance teams developed jig systems to quickly align damaged hull components. They created modular test stands for engines and transmissions. They established parts management systems that tracked every salvageable component from damaged tanks. Once systematized, these repair protocols became force multipliers. German commanders had planned for a war of quality versus quantity, expecting superior tank design to offset American production advantages. They never anticipated the full implications of what American industry could achieve. Captured interrogation summaries revealed a stunning reality. German tank commanders were reporting inflated kill claims because they couldn't believe the same tanks were returning to battle. This wasn't propaganda. It was a documented disconnect based on industrial misconception. A tank seen burning one day could not possibly be back in combat 3 days later, yet American maintenance units were achieving exactly that. Field maintenance units refined their approach continuously. They developed tank recovery vehicles specifically designed to retrieve damaged Shermans under fire. They trained specialized repair teams that could swap an entire power pack in under 6 hours. They established supply chains that delivered replacement parts within 24 hours of request. None of these capabilities existed in comparable German units. By mid-1943, America was producing more tanks every month than Germany had produced in the entire year before the war. Factory output reached 2,000 tanks monthly. This wasn't merely a numerical advantage. It represented a fundamentally different understanding of modern warfare. For the first time in military history, a weapon system was being treated as a consumable resource rather than a precious asset. The Germans measured success by kill ratios, proudly claiming 5 Shermans destroyed for every Panzer lost. The Americans measured success by ground taken and held, regardless of equipment losses. A Panzer that destroyed 5 Shermans before being knocked out resulted in 5 replacement Shermans arriving from the factories, while the Panzer remained a permanent loss. The symbol of American industrial mobilization had become an unstoppable force, not through technological superiority, but through the cold mathematics of production capacity. America's factories were delivering tanks faster than Germany's gunners could. Destroy them. October to December 1943, Ukraine Eastern Front. A Wehrmacht maintenance depot near Zhytomyr displayed a disturbing contrast. 12 knocked-out Panzer IVs stood in various states of disassembly, while Soviet T-34 and American-supplied Shermans continued pressing westward. The German tank commander's report laid bare the mathematical impossibility they faced. Enemy armor destroyed in sector, 37 confirmed kills. Yet enemy strength increases daily. Our 14 operational Panzers now face approximately 55 Allied tanks in the same sector. This wasn't an isolated incident. Across the eastern and western fronts, German commanders reported the same phenomenon. Tactical victories turned into strategic defeats because Allied tanks simply kept coming. A Panzer battalion commander noted with growing alarm, "We achieve favorable exchange ratios of 4-to-1 or better, yet find ourselves outnumbered within days. American production capacity has fundamentally changed the equation of armored warfare." The growing realization among German tank crews was profoundly demoralizing. SS Panzer Grenadier Hans Müller wrote in his field diary, "Recovered after the war. Our tank destroyed 5 Shermans last week near Korosten. We thought we'd earned a respite. Today we faced 12 fresh Shermans with new crews. It's as if they have an endless supply while we fight with the same machines for months, patching them together with whatever parts we can scavenge." By late 1943, the Sherman's presence on both the western and eastern fronts created a strategic vice that German forces couldn't escape. In Italy, North Africa, and the Soviet Union, the same green-painted medium tanks rolled forward in seemingly endless waves. The psychological impact was devastating. German tank crews began calling the Sherman the coffin for 5 brothers, not because it was especially deadly, but because they knew that destroying one meant facing 5 more the next day. Technical analysis of field. Reports revealed the core asymmetry. The average German panzer required 300,000 man-hours to produce. Specialized machining, hand-fitted components, and limited production facilities created bottlenecks throughout the manufacturing process. The Sherman required just 40,000 man-hours, less than 15% of the German effort, and those hours were distributed across a manufacturing base 10 times larger than Germany's. American General George Patton understood this industrial advantage perfectly when he told his troops, "The way to win is to make the other poor dumb bastard die for his country. We're going to advance constantly and we're not interested in holding anything except the enemy's balls. We're going to twist his balls and kick the living hell out of him all the time." This wasn't bravado, it was mathematical certainty. American tanks could advance aggressively because losses were replaceable. German tanks had to be preserved because each loss was nearly irreplaceable. The cause and effect relationship became brutally clear. Production velocity created tactical freedom. Tactical freedom allowed aggressive maneuvers. Aggressive maneuvers maintained constant pressure. Constant pressure prevented enemy reorganization. The Sherman wasn't just a tank, it was a manufacturing philosophy translated into steel, imposing America's industrial might directly onto the battlefield. Field reports from the Eastern Front documented this pressure. One Panzer Division reported losing 17 tanks in 3 days of fighting near Kiev. Those losses represented nearly 2 months of Germany's total tank production. In the same period, the opposing Soviet and American forces lost 31 tanks, representing less than a week of Allied production. The mathematics were implacable. A captured German intelligence assessment dated November 1943 showed growing desperation. American factories now produce more Sherman tanks every 2 days than our entire monthly output of all tank types combined. This production disparity cannot be overcome through tactical superiority alone. The admission was stark. Germany's qualitative edge couldn't compensate for America's quantitative flood. By winter 1943, German tank crews developed a grim new ritual. After destroying a Sherman, they wouldn't celebrate. Instead, they would immediately begin counting how many more would appear to replace it. The psychological burden became unbearable. Panzer Commander Karl-Heinz Böhm wrote after the war, "We no longer felt satisfaction when destroying American tanks. We felt only a momentary reprieve, knowing that tomorrow we would face twice as many. It was like trying to empty the ocean with a teacup." Allied planners recognized this psychological advantage and exploited it mercilessly. Damaged Shermans were dramatically dragged off the battlefield, often within view of German positions. Hours or days later, freshly painted replacements would appear in the same sector. The message was unmistakable. Your victories are temporary. Our resources are limitless. January to April, 1944, Anzio, Italy. The desperate fighting around the Allied beachhead demonstrated the Sherman's true strategic value. Records from the U.S. 1st Armored Division documented the mathematical reality. Tank losses during breakout operations, 118, M4 Shermans. Replacements received within 14 days, 126 new tanks. The German 14th Panzer Corps opposing them lost 43 tanks during the same period, but received only 17 replacements. Tactical superiority meant nothing when outproduced 7-1. German commanders shifted to increasingly desperate countermeasures. They concentrated their limited tanks in smaller areas, trying to create local numerical superiority. They prioritized anti-tank guns and mines, hoping to increase Sherman losses beyond America's ability to replace them. They developed ambush tactics to maximize kill rates. None of these approaches changed the fundamental equation. American factories in Detroit, Lima, and Grand Rapids were producing Shermans faster than German gunners could destroy them. When a German tank was lost, it created a permanent reduction in combat power. When an American tank was lost, it represented a temporary setback quickly remedied by the next supply ship. The production numbers told the story that tactical reports couldn't capture. By early 1944, Monthly Sherman production regularly exceeded 2,000 units. German Panzer production struggled to reach 250 tanks per month. Even accounting for tanks sent to the Pacific or supplied to other Allied nations, the Western Front was receiving 5 new Shermans for every new German tank. This production advantage translated directly into battlefield flexibility. American commanders could afford to take risks that their German counterparts couldn't contemplate. A failed attack might cost 20 Shermans, easily replaceable. A failed German attack might cost 5 Panzers, a crippling loss that couldn't be restored for months. The psychological burden on German tank commanders became crushing. Oberst Werner Frobe of the 15th Panzer Division wrote in his operational summary, "Our crews achieve remarkable success against numerically superior forces, but morale suffers as they watch destroyed enemy tanks replaced within days while our losses remain permanent. The knowledge that American factories produce more tanks each month than we have on the entire Italian front creates a sense of inevitable defeat." The cause and effect relationship was now reflected in strategic planning. German forces increasingly adopted defensive postures, attempting to preserve their irreplaceable tanks. Allied forces pursued aggressive maneuvers, knowing their losses would be quickly restored. This asymmetry shaped the entire campaign. Defense yielded territory, lost territory reduced strategic options. Reduced options accelerated defeat. Allied intelligence actively exploited this psychological advantage. Propaganda broadcasts aimed at German tank crews emphasized production statistics. Leaflets dropped behind enemy lines included photographs of Sherman assembly lines with captions like, "Today's production, 80 tanks." "How many did your factories build today?" The intended message was clear: resistance is mathematically futile. By spring 1944, German tank crews reported a new and disturbing development. The Shermans they faced were increasingly equipped with upgraded 76mm high-velocity guns capable of penetrating Panzer IV armor at combat ranges. This wasn't a technological breakthrough. The gun had been available since 1943. The timing reflected America's production philosophy. Improvements were introduced only when they didn't disrupt manufacturing flow. The M1A1 76mm gun required a larger turret, which had been designed and tested by Mid-1943. But introducing it immediately would have required retooling multiple factories and reducing output temporarily. Instead, American planners continued producing the original 75mm gun version while perfecting the manufacturing process for the upgraded model. Only when production capacity was secure did they begin transitioning to the improved version. This approach reflected a fundamental difference in industrial philosophy. German engineers pursued qualitative improvements regardless of production impacts. American engineers balanced improvement against production disruption, prioritizing consistent output over incremental capability gains. The result was a steady flow of adequate tanks rather than irregular deliveries of excellent ones. German intelligence reports from April 1944 noted this shift with growing alarm. Enemy tanks now appearing with long-barreled guns similar to our WK-40. Previous armor advantage diminished. Sherman quantity unchanged despite upgrade. The qualitative gap was narrowing while the quantitative gap remained unbridged. German tankers now faced both more tanks and better tanks. May to June 1944, Eastern France. A Waffen SS maintenance company struggled to repair damaged Panthers near Nancy. Spare parts were virtually non-existent. Critical components like transmissions and final drives were unavailable. Factory support had dwindled to occasional shipments of inadequate quantities. The maintenance officer's report outlined the dire reality. 7 Panthers non-operational due to parts shortages. Estimated repair time, indefinite. American bombing has severely impacted factory output. The contrast with Sherman maintenance operations was stark. American repair depots received regular shipments of complete power packs, transmissions, suspension components, and even entire turrets. Standard practice was to replace rather than repair, faster and more reliable in combat conditions. A Sherman with a damaged engine could have the entire power pack replaced in 4 hours and return to combat the same day. This maintenance asymmetry created a multiplier effect for American production advantages. Not only were more Shermans being built, but damaged ones were returning to service at rates German maintenance officers found impossible to match. By mid-1944, the effective ratio wasn't just the 5-to-1 production advantage, but closer to 8-to-1 when accounting for recovery and repair capabilities. D-Day and the subsequent breakout operations demonstrated this advantage in brutal clarity. During the first 2 months of the Normandy campaign, American forces lost approximately 640 Shermans. During the same period, they received over 700 replacements. German panzer units lost approximately 250 tanks and received fewer than 100 replacements. The mathematical trajectory was clear and irreversible. German commanders recognized the implications immediately. General Heinz Guderian, Inspector General of Armored Troops, wrote in his situation assessment of July 1944, "Our current monthly production satisfies barely 20% of frontline requirements. American industry delivers more tanks each week than we receive each quarter. This production disparity determines the strategic outcome, regardless of tactical performance." German tank crews developed increasingly elaborate ambush tactics, hoping to maximize kill ratios and somehow overcome the production imbalance. They utilized terrain advantages, prepared multiple firing positions, and coordinated with infantry anti-tank teams. These tactical innovations occasionally produced local successes. A Panther might destroy 6 or 7 Shermans in a single engagement, but the strategic equation remained unchanged. For every successful ambush, 3 more failed. For every Panther that survived to fight another day, 2 were lost to mechanical breakdown, air attack, or artillery. For every Sherman destroyed, 3 more arrived from the coastal supply dumps. The mathematics of attrition were relentless and unforgiving. By August 1944, the balance had shifted beyond recovery. American tank crews understood this advantage intuitively. Sergeant William Freitag of the 2nd Armored Division wrote in a letter home, "We know their Panthers can kill us if they hit us first, but there are always more of us than them, and we keep coming no matter how many they knock out. They have to be perfect every time. We only have to be lucky once. Those aren't odds I'd want to face from their side." The psychological impact on German tank crews deteriorated further as Allied air superiority increased. Shermans operated with constant air cover, while German tanks could move only at night or in bad weather. This operational constraint further reduced the effectiveness of Germany's already outnumbered tank force. A Panther might be technically superior to a Sherman in a direct engagement, but it couldn't influence battles it couldn't reach. September to October 1944, Belgium-German border. The devastating fighting around Aachen demonstrated the final evolution of the Sherman's numerical advantage. Operational records from the U.S. 3rd Armored Division documented the mathematical end state. Tank strength maintained at 90% of authorization despite heavy combat. Replacement pipeline now delivering tanks within 48 hours of requisition. The German panzer brigades opposing them operated at approximately 35% of authorized strength. With the front line now approaching Germany itself, the production disparity became even more pronounced. American tanks still traveled from factories to the front via secure supply lines. German tanks had to run a gauntlet of Allied air attacks, even to reach their own troops. Some Panther and Tiger units reported receiving new tanks only to lose them to air attack before they reached the combat zone. The cause and effect chain was now terminal. Production advantages created numerical superiority. Numerical superiority allowed constant pressure. Constant pressure prevented reorganization or recovery. Prevention of recovery accelerated collapse. By autumn 1944, the outcome was mathematically inevitable, regardless of individual tank quality. German attempts to reverse this equation through qualitative improvements failed to change the strategic balance. The introduction of the Tiger II, King Tiger, with its formidable 88mm gun and 150mm frontal armor, created a tank that could destroy Shermans with near impunity in a direct engagement. But Germany built only 489 Tiger IIs during the entire war, equivalent to 1 week of Sherman production. The final irony came in early 1945, when American factories began delivering the M26 Pershing heavy tank with a 90mm gun and armor protection comparable to the Panther. This tank had been ready for production much earlier, but was deliberately delayed because it would have disrupted the Sherman production lines. Only when victory was assured did American planners approve the transition to the improved design. This decision reflected the underlying industrial philosophy that had shaped the entire campaign. Germany built the best tanks it could and never had enough. America built adequate tanks in overwhelming numbers. The Sherman was never intended to win tank versus tank duels. It was designed to win campaigns through unstoppable production volume, and it succeeded completely. November 1944 to February 1945, Western Germany. Production records from remaining German factories displayed the final collapse. One column listed theoretical output targets, hundreds of Panthers and Tigers demanded by Berlin. The adjacent column documented reality: single-digit weekly deliveries, sporadic parts shipments, and depleted material stockpiles. Berlin's orders still demanded both quality and quantity. The Wehrmacht's planning staff issued production requirements as if Germany's industrial base remained intact. Factories were expected to deliver both upgraded designs and increased output. The reality was industrial disintegration. Allied bombing had reduced production capacity by more than 70%. Critical materials like manganese, chromium, and molybdenum were exhausted. Machine tools were damaged or destroyed. Skilled workers were dead, drafted, or evacuated. Power generation was intermittent at best. Factory dispersal to underground facilities created logistical nightmares that further reduced output. Some tank components traveled hundreds of kilometers between manufacturing steps, with each journey vulnerable to air attack. A factory controller's memo from January 1945 stated bluntly, "Monthly output reduced to approximately 40 Panthers and 25 Tigers across all facilities. Steel alloy shortages critical. Armor plate production prioritized for bunkers rather than vehicles." Meanwhile, American factories continued delivering over 2,000 Shermans monthly without interruption. The cause and effect relationship was now absolute. Germany could barely replace 5% of its monthly tank losses. America could replace 150% of its losses, actually increasing tank strength even during heavy might-is-relation combat operations. German units operated at 25–30% of authorized strength. American units maintained 95% of their paper strength regardless of battlefield losses. Field units received these diminishing shipments with growing desperation. Tank battalion commanders attempted to distribute their few operational vehicles where they could have the greatest impact. But this concentration created its own vulnerability. American forces simply avoided the strong points and attacked where German tanks weren't present. By January 1945, many German tank crews had adopted a fatalistic philosophy. Lieutenant Hans Schäfer of the 9th Panzer Division wrote in his final report before being captured, "We no longer count our kills. What does it matter if we destroy 10 Shermans today when 20 more will arrive tomorrow?" The Americans don't need to win battles. They simply need to keep coming, and they know it. Production numbers remained high on official German reports. Berlin could claim industrial output was continuing. Warehouses held stacked armor plates and partially completed hulls, but those numbers and those stacks meant nothing if complete tanks couldn't reach the front. Germany's tank force had reached the final stage of industrial collapse. They could still manufacture some components, still assemble some tanks, but they could no longer match even 10% of American production. By February 1945, Germany could still build tanks in the statistical sense, but it could no longer influence the campaign through armored warfare. The Sherman had achieved its strategic purpose not by outfighting German tanks, but by simply outlasting them. March to May 1945, American and Soviet occupation zones, Germany. Captured German tank factories sat silent beside Allied technical inspection teams. Engineers recorded manufacturing techniques, metallurgical standards, and design philosophy. The expectation among American Army ordnance personnel was that German tanks would show superior craftsmanship and engineering. Testing would reveal exactly how much quality had been sacrificed for American quantity. Results split the assessment sharply. German designs demonstrated excellent theoretical engineering. The Panthers' sloped armor, high-velocity 75mm gun, and torsion bar suspension represented excellent tank design. The Tiger's armor protection and long-range accuracy were impressive. On paper, both outclassed the Sherman in tank versus tank combat, but practical engineering told a different story. Late-war German tanks showed critical weaknesses in transmissions, final drives, and engine reliability. Panthers typically required major drivetrain overhaul after 150 kilometers of operation. Shermans regularly operated for 1,500 kilometers between overhauls. A Tiger's transmission was so complex and fragile that more were lost to mechanical failure than to enemy action. German designs prioritized theoretical performance over practical reliability. American designs made the opposite trade-off. The Sherman's Continental R-975 radial engine was less powerful than the Maybach engines in German tanks, but vastly more reliable. The Sherman's VVSS suspension wasn't as smooth as German torsion bar systems, but was simpler to maintain and repair. Engineering reports documented in United States Army Technical Manual TME 30-451 from 1945 summarized the findings. German tank design demonstrates excellent theoretical capabilities, but practical shortcomings in reliability, maintainability, and production efficiency. American emphasis on standardization, simplified manufacturing, and field serviceability proved strategically decisive despite tactical limitations. The cause and effect conclusion was definitive. Germany's pursuit of qualitative superiority created tanks that were too complex to manufacture in necessary quantities. America's focus on quantitative advantage produced tanks that were simple enough to build by the tens of thousands. The German approach might win individual tank duels, but the American approach won the war. Allied technical judgment shaped post-war tank development profoundly. Future American designs would incorporate some German innovations, but maintain the fundamental philosophy that had proven successful: standardization, reliability, and production efficiency. The M26 Pershing and subsequent M48 Patton series balanced combat performance with manufacturing practicality. The final irony was that German engineers had understood the production problem all along. Captured documents revealed repeated warnings from manufacturing experts about the risks of complexity. In 1943, the German Armaments Ministry had actually proposed a simplified Panther II, design with interchangeable components and streamlined production methods, essentially adopting the American approach. Hitler personally rejected the concept, insisting on qualitative superiority regardless of production consequences. By May 1945, the mathematical conclusion was inescapable. The Sherman tank had achieved what Hitler feared most: the full mobilization of American industrial might against Germany. It wasn't the best tank of World War II by most technical measures, but it was the most decisive tank, the one that arrived in such overwhelming numbers that quality advantages became irrelevant. The final production tally told the complete story of the Sherman tank's rise and the German Panzer forces' fall. Total production: 49,234 Sherman tanks, built between 1942 and 1945. Of the German designs it faced, 5,976 Panzer IVs, 5,508 Panthers, and 1,347 Tigers. Combined, all German tank production during the entire war barely exceeded half of Sherman production alone. June to August 1945, Aberdeen Proving Ground, Maryland. Captured German Panther and Tiger tanks sat in rows beside dozens of Sherman variants. Engineers recorded detailed performance measurements, AAT, acceleration, fuel consumption, maintenance requirements, and reliability statistics. The expectation among American generals was straightforward. Now that the war was won, it was time to assess what had been sacrificed for production speed. Testing would reveal exactly how inferior the Sherman had been to its German counterparts. Results painted a nuanced picture that challenged simplistic narratives. In tank versus tank combat at typical European engagement ranges of 700 to 900 meters, the Panther and Tiger were undeniably superior. Their high-velocity guns could penetrate Sherman frontal armor while remaining immune to the standard Sherman 75mm gun from the front. This advantage was real, but narrower than German tankers believed. When factors beyond gun and armor were considered, the picture changed dramatically. Sherman tanks demonstrated 90% mechanical reliability during extended testing. Panthers achieved only 55%, Tigers barely 45%. For every hour of combat operation, the Sherman required 7 hours of maintenance. The Panther needed 4 hours. The Tiger, an astonishing 8 hours. One testing officer noted, "A technically superior tank that breaks down before reaching the battlefield has an effective combat value of 0. Fuel consumption testing revealed another critical advantage. The Sherman's operational range of approximately 120 miles on internal fuel matched typical tactical requirements perfectly. The Panther's range of 62 miles and Tiger's 68 miles meant German units constantly struggled with refueling logistics. This limitation reduced strategic mobility precisely when Germany needed operational flexibility to counter Allied numerical superiority. Ergonomics testing yielded surprising results. Sherman crews could exit their tank in an emergency in an average of 9 seconds. Panther crews required 17 seconds, Tiger crews 22 seconds. This seemingly minor detail had profound battlefield implications. A damaged Sherman crew had double the survival probability of their German counterparts. The difference between life and death often came down to those precious seconds. One engineering report captured the philosophical contrast perfectly. German designs optimize for theoretical combat performance at the expense of practical battlefield utility. American designs optimize for consistent performance across all operational requirements. The Tiger excels in carefully controlled combat scenarios, but falters under real-world constraints. The Sherman maintains adequate performance across all conditions. The report continued with a striking observation. Interviewed Sherman crews express confidence in their vehicle's reliability and maintainability despite acknowledging its combat limitations. Captured German tank crews express frustration with their vehicle's mechanical unreliability despite pride in their combat capabilities. This psychological factor significantly impacts crew performance and tactical decision-making. This revelation reframed the entire technical debate. The Sherman wasn't designed to win individual tank duels. It was designed to win campaigns through consistent, reliable performance at every level from factory to battlefield. The true measure wasn't penetration tables or armor thickness, ETI. It was the integrated system of production, transportation, maintenance, and employment that delivered combat power where and when needed. General George Patton, who had led Sherman-equipped armored divisions across France and Germany, summarized this philosophy bluntly. In war, the only thing better than a good weapon is enough of a good weapon. The Sherman gave us enough, and it was good enough. That's all that matters when you're winning. September to November 1945, Detroit, Michigan. Production lines that had delivered thousands of Shermans now stood idle as workers returned to civilian manufacturing. The cavernous factory spaces of the Detroit Tank Arsenal, Lima Locomotive Works, and Pullman Standard retained the ghosts of their wartime purpose, assembly jigs, overhead, cranes, and the faint outline of tank tracks on concrete floors. The human side of the production miracle emerged in post-war interviews with factory workers. Mary Jenkins, who had worked as a welder at the Detroit Tank Arsenal, recalled, "We knew exactly what we were building and why. Every tank that rolled off our line meant American boys had a better chance of coming home. We weren't just assembling machines, we were saving lives, one Sherman at a time." This connection between factory and front line was far more direct than German workers experienced. American tank factories regularly received letters from tank crews in the field, sometimes with photographs of their Shermans in action. Factory tours by wounded veterans created emotional links between those who built the tanks and those who fought in them. The psychological impact was profound. Production wasn't abstract, it was personal. Rose Wilson, who had supervised transmission assembly at Lima Locomotive Works, described the competitive spirit that drove production records. "We had boards showing daily output for each shift. Nobody wanted to be the shift that fell behind. When we heard about big battles brewing in Europe, we'd push even harder. We set a record of 18 complete Shermans in a single shift after learning about the Normandy landings. Everybody stayed late, nobody complained." This human element of production was something German industry never managed to harness effectively. While German factories remained technically proficient, they never achieved the psychological mobilization that American industry created. The difference wasn't in machine tools or engineering drawings, it was in the human commitment to production as a patriotic duty. A post-war industrial analysis documented this contrast. American production philosophy integrated human motivation with technical efficiency. Workers understood their role in the larger war effort and identified personally with production goals. German production remained technically excellent, but emotionally disconnected from national purpose, particularly as defeat became increasingly probable. The analysis continued with a striking observation. American factories improved efficiency throughout the war, with man-hours per tank declining steadily from 1,942 to 1,945. German factories showed declining efficiency during the same period, with increasing man-hours per tank despite growing experience. This divergence reflects fundamental differences in worker motivation and management approach. December 1945 to February 1946, Pentagon, Washington, D.C. Military analysts compiled the final statistical assessment of tank warfare on the Western Front. The numbers told a story that transcended tactical debates about individual tank performance. Sherman tanks produced 49,234. German tanks of all types produced 26,925. Sherman tanks deployed to European theatre, 20,597. Sherman tank combat losses, 4,177. Ratio of production to loss, 4:9:1. These figures revealed the true margin of American victory. Even if every Sherman sent to Europe had been destroyed twice over, production capacity would still have maintained numerical superiority. The margin was so overwhelming that technical debates about armor thickness or gun penetration became strategically irrelevant. America hadn't just won the production race, it had rendered the race meaningless through sheer industrial scale. A senior War Department planning officer summarized this lesson. The Sherman represents a fundamental strategic insight. Adequate quantity consistently delivered is more decisive than excellent quality sporadically available. Future weapons development must balance technical performance against production capacity, recognizing that the perfect weapon that can't be built in sufficient numbers is ultimately inferior to the good weapon that can. This insight shaped American military procurement for generations. Future tanks like the M47 and M48, Patton, M60, and eventually the M1 Abrams would incorporate lessons from both American and German design philosophies. They would pursue technical excellence but never at the expense of producibility, reliability, and maintainability. The Sherman's legacy wasn't its combat performance, it was the strategic philosophy it embodied. The human dimension of this philosophy emerged in post-war interviews with tank crews. Staff Sergeant James Miller, who had commanded a Sherman in the 2nd Armored Division, reflected, "We knew the Panthers could kill us if they got the first shot, but we also knew there were always more of us than them. If we lost 2 tanks taking out 1 Panther, we still had plenty left while they had nothing. It's a cold calculation, but that's what winning looks like." This battlefield mathematics created a psychological edge that transcended technical specifications. American tank crews fought with the confidence that their losses were replaceable. German crews fought with the knowledge that each loss represented an irreplaceable reduction in combat power. That psychological difference affected tactical decisions, risk acceptance, and ultimately combat effectiveness. Technical analysts studying this phenomenon noted, German tank crews exhibited increasing tactical caution as the war progressed, attempting to preserve irreplaceable vehicles. American crews maintained aggressive tactics throughout, accepting losses as an inevitable cost of victory. This behavioral divergence stemmed not from training differences but from each side's accurate assessment of their strategic situation. March to May 1946, Nuremberg, Germany. During the war crimes trials, interrogations of German industrial leaders revealed the full extent of their misunderstanding of American production capacity. Albert Speer, Hitler's armaments minister, admitted, "We simply could not believe the production figures our intelligence services reported. 40,000 Sherman tanks viewed technical specifications as a means to create producible weapons. The Sherman wasn't just a tank, it was the physical embodiment of American industrial pragmatism." June to August 1946, Detroit and Washington, D.C. As the American economy transitioned to peacetime production, military planners and industrial leaders compiled the lessons learned from the Sherman's success. These lessons would shape both military procurement and civilian manufacturing for generations to come. Standardization enables mass production. The Sherman's highly standardized design allowed multiple manufacturers to produce interchangeable components, creating production capacity far beyond what specialized designs could achieve. Reliability trumps theoretical performance. A tank that operates consistently under all conditions delivers more combat power than a superior tank plagued by mechanical failures. Maintenance accessibility determines battlefield availability. Sherman components were designed for easy access and rapid replacement, minimizing downtime and maximizing combat presence. Production velocity creates strategic freedom. The ability to replace losses quickly allows more aggressive tactics and operations than would be prudent with limited replacement capacity. Human factors affect both production and employment. Worker motivation in factories and crew confidence in combat are critical factors that technical specifications cannot capture. These principles were codified in military procurement regulations and industrial best practices. The legacy of the Sherman wasn't just the tank itself, but the manufacturing philosophy it represented, a distinctly American approach that valued practical results over theoretical perfection. A War Department strategic assessment in August 1946 concluded, "The decisive factor in the European theatre was not technological superiority, but industrial capacity correctly applied to battlefield requirements. Future conflicts will be won by nations that can most effectively translate industrial potential into deployed combat power." The Sherman tank represents the successful application of this principle on an unprecedented scale. This assessment proved prophetic. Cold War military planning on both sides emphasized production capacity alongside technical capabilities. The Soviet Union would adopt many American mass production techniques, while NATO forces balanced technical sophistication with production considerations. The ghost of the Sherman influenced tank design long after the last M4 left active service. September 1946, Fort Knox, Kentucky. As the U.S. Army established its peacetime training programs, the lessons of Sherman production were institutionalized in officer education. Major General I.D. White, commanding the Armored Center, emphasized this perspective. "Gentlemen, Remember that the finest tank in the world, sitting in a factory, is worth less than the most ordinary tank on the battlefield. Numbers matter, production matters. The Sherman wasn't the best tank of the war, but it was the tank that won the war. This pragmatic perspective shaped a generation of military officers who would later lead during the Cold War. They understood that military power wasn't measured by the theoretical capabilities of individual weapons, but by the integrated capacity to deliver combat power where and when needed. The Sherman had demonstrated this principle more clearly than any weapon system in history. The human dimension of this lesson emerged in interviews with tankers who had fought in both Shermans and captured German tanks. Technical Sergeant William Harrison of the 761st Tank Battalion recalled, "We captured a Panther near Kassel in '45 and used it for about 3 days. Tremendous gun, great armor. But it broke down twice, and nobody knew how to fix it. We went back to our Shermans and kept moving." That tells you everything you need to know about which tank actually worked in the real world. This practical battlefield experience validated what production statistics had already proven. The Sherman succeeded not because it was the best tank in theoretical terms, but because it was the most effective tank in practical terms. Its combination of adequate combat performance, mechanical reliability, and overwhelming numbers created a combat capability that technically superior German designs could not match. The final assessment came from General Dwight D. Eisenhower, who had commanded all Allied forces in Europe. The Sherman tank was one of the most decisive weapons of the war, not because it was the best tank, it wasn't, but because it was good enough, and we had thousands of them. That's the nature of industrial war. You don't need the perfect weapon. You need enough of a good weapon. This perspective would guide American military procurement for decades. Future weapons systems would pursue technical excellence, but never at the expense of producibility and reliability. The lesson of the Sherman had been learned at tremendous cost, and it would not be forgotten. The tank that German crews couldn't believe kept coming had permanently changed the mathematics of modern warfare. As German Panzer commander Colonel Hasso von Manteuffel had observed in his post-war assessment, the Sherman wasn't the best tank. It was just the right tank in the right place at the right time in seemingly infinite numbers, and that, ultimately, is what matters in war. That industrial miracle, 234 tanks in 4 years, represented more than just production statistics. It represented American workers, factory towns, railroads, steel mills, and an entire nation mobilized to defeat fascism with an overwhelming tide of tanks that German crews watched in disbelief, rolling endlessly toward them across the battlefields of Europe. The ultimate triumph wasn't technical, it was mathematical, and the mathematics of Sherman production proved irresistible. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.